Hey everyone, welcome to this lecture for PhD 105, a course on data science. This is the second in a collection of 3 videos on linear models, a very general framework for doing data analysis. This video in particular is about comparing models using cross-validation. I'm going to start by giving an introduction using slides, and after that, I'll demonstrate the material in a screencast. Feel free to skip around to the parts you find most useful, and to get the most out of this, I encourage you to code along. All the material is available at phd105.com, and there are links in the description below. Awesome. Let's get started. Cool. So I'm going to try to explain what cross-validation is and why we might want to do it. The problem that cross-validation is intended to help with is one of model selection. The basic idea for model selection is the following. You know you're going to build a model. You've got a outcome on one side and you've got your predictors on another side, and you have to sort of figure out what are the things that you want to put into your model and what structure do you want that to have. Now, in the very best case scenario, you know a lot of what you need to put into your model. You know what confounders you have a clear understanding of what structure that is going to take, and there's maybe one predictor that you're interested in. You want to know the effect of this variable in the context of a model that you care about. And I say that this is the best case because it's the one where like statistical inference really works the way that it's supposed to. You don't have to worry about multiple comparisons. You don't have to worry about how you got to the model that you ended up with. There's sort of nothing going on there. What you're left with though is just like that one hypothesis test that you care about. You can think about this another way. If you were going to do like a randomized trial, you know that you've randomized everybody and you're just interested in whether or not some exposure, some intervention, whether or not that has an impact that you're interested in, and that's a real clear hypothesis test. Generally though, that's not what happens. A lot of times what you're left with is an awful lot of predictors and a lot of different ways that those predictors might be combined and ways that you might sort of express the impact of individual pieces of those. You might have sort of a curve for one variable, and you might have sort of a step function for another one. You might get some interactions. You might get all kinds of stuff going on the right-hand side of your model, and you have to figure out among all of the possible models that you want to create, which is the one that you're gonna actually produce for relating your outcome to the predictors that you have available to you. I always want to include a caveat here. You're going to build a model, and I don't want you to think of that model as the true thing. This is your approximation. This is the thing that you use to sort of say, well, I think the universe kind of looks like this. It probably doesn't exactly look like this. It's not true that I'm describing what the universe is actually doing behind the scenes, but it's a close enough approximation. And I think that's to keep in mind that no model is true, but some of them are useful is sort of the adage. It's almost a cliche among statisticians, and it's definitely a useful perspective to have. So great, we got to figure out what's going to go on the right hand side of the model. Okay, this is a hard problem. If it were easy, we wouldn't have to worry about it so much. But it's not. There are lots of ways that you could specify a model, and in the end, some of those ways are probably going to be better, and some of those ways are going to be worse. And you have to figure out how that is, and you have to figure out how you're going to make that comparison. So you may be familiar if you've done some sort of standard traditional model building and statistical coursework. You might be familiar with this idea about using nested models. You're going to sort of take a predictor and add the next thing and then add the next thing. And you can always compare a larger model to a smaller model and see whether or not that is statistically significantly better. In that context, you do have to be worried about multiple comparisons. You do have to be sort of worried about whether or not the p-values you get at the end of that are actually valid. They're not. To put it shortly, I mean, things like forward and backward stepwise selection are sort of bad for that reason, that you're following along a particular path and you find yourself at the end and all the p-values that you get sort of don't make sense. That's, again, maybe a something to worry about somewhere else, but that's one approach. You have statistical tests, though, is what I'm saying in that case. You can sort of build up comparing models that are nested within each other using statistical tests, and sometimes that's helpful. If you have non-nested models, though, there aren't statistical tests you're going to do. You're not going to get p-values for things that are non-overlapping, but you can do things like AIC and BIC, something like that says how well do I fit the data using something like a residual sum of squares, and then how much stuff has gone into my model, something about the number of predictors that is in there, and you try to find a model that balances those two things, goodness of fit with complexity. Okay. A lot of what model selection boils down to is asking questions about that, right? Like, how good is my my fitted values, and is my model complex enough or too complex? And a lot of the ways that you might frame these questions are really related to each other. So if you have a model that isn't complex enough, then you're sort of missing patterns in the data that exist. And if you have a model that's too complex, you're chasing individual points that are sort of really actually random fluctuations. And that's sort of very similar to saying, am I underfitting what's going on now? Is there's like some pattern that I need to get and I'm not quite fitting enough? Or am I overfitting? Am I chasing randomness? Do I have high bias? Do I have high variance? These are all very similar questions. Now, there's another way that you might pose this question and think about how you're going to compare model performance. And the way that I would suggest that you might consider this is to say, does the model that I have produced now give me good predictions on future data sets? Does it generalize to some data that I might get in the future? And if the model that I have now gives me good predictions on data I haven't seen, well, then it's probably not underfitting and it's probably not overfitting. It's probably doing just about right. And that's sort of the goal for cross-validation, is to figure out how you can answer the question of whether or not a model is going to generalize to a future data set. This is the kind of figure that you end up with where on the y-axis what we're looking at is prediction accuracy, right? I'm sort of thinking of generalizability in a very specific sense. Can I take a model generated on one data set and make accurate predictions for outcomes in another data set? That's what I'm really interested in. And if I don't have a model that's complex enough, then what I end up with is underfitting. There are patterns that I'm missing, and I do bad in terms of prediction accuracy. And if I end up with a model on the other side where I've got too much complexity, I'm chasing things that are actually random fluctuations, I'm calling something a pattern when it really isn't, well, then I'm also going to make bad predictions because that random fluctuation isn't going to exist in a new data set. And if I can find the point right in the middle between those two things, then I'm going to balance underfitting and overfitting. I'm going to get exactly the right patterns, and I'm not going to chase any noise, and I'm going to get exactly the right model right there in the middle. And when I say I'm going to get exactly the right model right there in the middle, what I mean is sort of that you're going to have the most accurate predictions. And now that I'm sort of looking at this, I think prediction accuracy is maybe not exactly the right thing here. Really, I'm sort of thinking about prediction error. So low prediction errors are better and high prediction errors are worse, and you're sort of trying to get low prediction errors. So ideally, this is something that you could do in real life. Ideally, what you would do is sort of gather one data set and build your model, maybe build a couple of models, and you're going to say like, all right, these are things that I think are pretty good. And now I'm going to go out into the world and I'm going to get a new data set from the same population. I'm going to gather new data, and I'm just going to take the models that I constructed over here, and I'm going to apply them to my new data set, and I'm going to see whether or not they give me reasonably accurate predictions. And if they do, well then great, I'm happy with a model. Now, of course, this is not how the world works. You're not going to gather a data set and then go out into the world and gather a new data set from the same population in exactly the same way and just check whether or not your model is being generalizable. That's not really what happens. So the solution here is to just sort of, you close your eyes and you act like it does. You make something up and you act like it does. And I'm sort of, I don't know, I guess maybe I'm being a little bit flippant here. So this is a principled thing that you can do, and it turns out that it works really well, and the process that it's trying to mimic is exactly this, of going out into the world and getting a new data set, and that's what we're going to try to do. So when I say go out into the world or act like we're able to go out into the world, really what I'm saying is the following. We're going to get a data set. This is the data that we've already collected, and we're going to randomly partition that into two new data sets, or we're going to randomly partition it into a training data set and a testing data set. If you put both of those together, you get the full data set, but you've separated them and they're sort of non-overlapping. And your training data is going to be the data that you use to build your model, and then your testing data is going to be the data that you're sort of acting as if it was drawn from the same population. You've gone out and you've gathered new data. You're going to build a model over here, and you're going to evaluate it over here. And how much goes into the training and how much goes into the testing is, different people have different ideas. I sort of like to keep 80% in my training data set and 20% in my testing data set. And in the context of linear models with continuous outcomes, the way that I'm going to evaluate prediction accuracy, the way that I'm going to sort of evaluate whether or not my model works is by looking at root mean squared errors. So I'm going to build a model over here, and then I'm going to use that model to make predictions over here, and I'm going to compare the predictions to the actual values, and I'm going to square those differences and divide by n and take the square root of that, right? So the idea here is sort of how well do my predictions hold up in a new data set? I've got a model, I generate predictions. How well do those predictions compare to the observed values? If my model isn't complex enough, it's going to be bad. If my model is too complex, it's going to be bad. But if my model is just right, then I'm going to be able to make accurate predictions. So I'm going to talk through that whole process again using this figure instead of just like waving my hands around. So again, you've got your full data set organized in a rectangle, and you're going to partition that into training and testing components. And here I'm sort of indicating these are going to be random elements. You're just going to sort of randomly split things into a training piece and a testing piece. You build your model on the training piece, and then you apply that model to the testing piece, and you generate the root mean squared errors. And really what you're going to be doing is building, say, 7, 8, 10, 12, 50 different models on training and evaluating each of those models on testing and seeing which one of those has the lowest root mean squared error. That's going to be the way that you solve this model selection problem, is by comparing the models that you think are plausible in terms of their prediction accuracy. So there are a couple of different ways that you might refine or expand on this idea of cross-validation. If I just sort of take my data set and I split it into 80% and 20%, there's some randomness in there, and sometimes one model is going to do better and another model is going to do worse. And if you did a different split, those two things sort of might switch in ranks. So often what happens is you do that 80-20 split and you just do that thing an awful lot of times. If you repeat that training split, you really get a sense of the distribution of root mean squared error comparing model A to model B, for example, and that gives you a better way to understand, is this just like a random variation, or is this actually a better performing model? So this is the process that I usually use, is to repeat the training and testing split and compare all my models. You can also use multi-fold cross-validation. You'll hear if you do 5-fold cross-validation, you divide your data into 5 buckets, use the first 4 buckets to predict the 5th one, and then the next 4 buckets to predict sort of the middle one. And so like each bucket is one time the thing that you're predicting, and the remaining times it's over here in your training data set. People like this, I don't love, but that's sort of a matter of choice. What's great about this is that cross-validation is a very, very general tool, right? So you can use cross-validation to compare not just a couple of models where are these the right confounders, is this the right predictor? You can compare all kinds of different things. You can compare traditional models to variable selection models to statistical learning models, and you can just check which one is giving me the best predictions. And in that sense, which one is going to be the most generalizable, the most useful thing for sort of making predictions moving forward. And the idea of cross-validation, even more than that, is sort of built in to a lot of modern methods for doing this kind of statistical analysis. And what I mean by that is in automated variable selection and in additive models and in regression trees and in a variety of other things, there are these things floating around that are called tuning parameters. And you have to pick a tuning parameter that works for lasso. And the process of choosing that tuning parameter often boils down to saying, like, well, let's try a bunch of different values of a tuning parameter and then pick the one that works best in terms of cross-validation prediction error. And that sort of, when I say cross-validation comes up a lot, that's sort of really what I mean. Now I want to comment briefly on a point that I made previously, which is that if you sort of are starting out from the idea that you are trying to generate statistical evidence in the sense of you want to have a p-value for a hypothesis test that tells you whether or not some exposure is related to some outcome, that's great. And if you can set up your model in such a way ahead of time where you know the list of confounders that you're going to be interested in and you can test the specific thing that you care about, that is in some sense the best case for generating statistical evidence in the context of a p-value. That's not the only way that you might go about generating evidence, and it often doesn't work out that way. But I do want to be clear about that if you want to get a p-value, you should be clear about the process that you're using to get to that point and make sure that it's valid in the way that you need it to be. Separately from all of that, though, separately from like whether or not p-values are even the right thing to do in the first place, I want to point out that prediction accuracy matters as a goal separate from statistical inference or statistical significance. If you build a model and you say, I think I've got all these confounders and you think they work, but then they don't make very good predictions and some other model structure actually makes really good predictions, well, we're not talking about a p-value and a difference between these two things, but it does give you some idea that the model you had started out with isn't really reflecting what's going on in the universe all that well, and this other model is making accurate predictions and it's probably better, so maybe you really do need to think about this. And again, that's different from talking about statistical significance, but making a comparison in terms of prediction accuracy can be an important thing to do. Cross-validation comes up a lot, and there are tools that we're going to use for implementing this. We saw the modeler package a little bit in the first video that goes along with this collection. In particular, we talked about add residuals and I think touched on add predictions. We're also going to build on some other things in there. Cross-VMC gives us a way of separating these training and testing splits, and RMSE computes a root mean squared error for a data set and a model. And we're going to be using those to sort of streamline the process of doing cross-validation. And if, like me, you sort of look at this and you think one training testing split is never going to be enough, well, you might want to repeat this an awful lot of times, and in that sense, using list columns and then mapping across things is a helpful thing too. So we're going to be focusing on the modeler package. I am also going to point out the tidyverse folks in the last couple of years have put a lot of effort into not just the modeler package, but a collection of packages referred to as tidy models. And the idea here is that in the same way that the tidyverse has dplyr and tidyr and ggplot and purrr and whatever else, tidy models has a collection of packages that sort of focus on very particular pieces of building regression models. Modeler is like a distillation of that we're going to use for now. You could probably spend a whole semester looking at tidy models and how this all works, and that's not really what we're focusing on today, but I feel like you should know that exists out there in the world. Okay, great. Let's go and do some cross-validation. Awesome. Let's get started doing cross-validation. I've got the usual infrastructure here, a new R Markdown page sitting in the project that has the same thing as linear models, and all the setup is the same as it always is. Before I get started on writing code for cross-validation, I want to talk a little bit about what I hope you get out of this video, because there's sort of going to be two things going on at the same time. What I hope you get out of this video is an understanding of how you can use prediction accuracy to compare models of varying degrees of complexity. And that if you understand that cross-validation, how that works, of partitioning things into training and testing, and then building models and then comparing whether or not those models work well in terms of prediction accuracy, that's great. To do that, we have to build some models that have varying degrees of complexity. And we're going to use some tools over here that allow us to build some models that are simple and some models that are complicated. And depending on sort of how much of statistical modeling you have in your toolbox, some of those tools might not make total sense right now. And I don't want you to get bogged down in wondering like exactly what an additive model is and how it's doing the things that it's doing. That's less important. The specific tools that we're using to build models that are complex is not something that I want you to be too worried about right now. What I want you to focus more on is, given that we can construct these models, how do we choose among them using prediction accuracy as a metric? So that's sort of what I hope we get out of today. We're going to start with a simulated data set, and then we're going to spend a little bit of time talking about an actual data set. And in all of this, really what we're trying to do is figure out how do you choose the right model, right? And I want to be clear that that's sort of our overarching goal, is picking the right model for a data set. So the data that I'm simulating here, I got to load packages, I always forget. The data that I'm simulating here, I'm sort of calling a nonlinear data frame. And the reason why is, let's look at the data. The data that I have constructed is nonlin df piped into ggplot, and let's put on the x-axis the x variable, and on the y-axis the y variable, and I'm just going to do geom point. Okay. Here's my data set. It's nonlinear, right? I could just sort of fit a line through this, and that's probably not going to work too well. If I knew at the outset, I know for sure that the way I'm generating this has a squared term. And so maybe if I fit a parabola, that'd be great. But if somebody just handed me this data set, I wouldn't know that it's a parabola. I would have to sort of figure out how much curvature is in there and what is sort of the right thing to do. And so this is sort of what we're trying to do. Now, the reason that I like this as an example is that it's easy to sort of talk about model complexity when looking at something like this. If I fit a straight line through there, that model is not complex enough, and it's going to make bad predictions in the future. And if I sort of started at this point and I just like connected the dots all the way through here, I got something that was really, really wiggly. Well, that's too complex. I'm doing too much stuff. I need to do less. If I can sort of fit something that goes kind of through the middle of these things and isn't too sensitive to an outlier here and not too sensitive to an outlier here, it's not chasing individual points. Well, if I can do that, then I'm probably going to make better predictions in the future than if I just go on a line or if I just sort of try to chase every little pattern that's in here, right? So that's really what we're going to be trying to do today, is at first figure out how we are going to how we're going to fit a curve through the middle of these data points and sort of pick the right curve that we might want to fit. Now, we're going to use cross-validation in two ways. Cross-validation by hand. And when I say by hand, I mean we're going to construct a training set and a testing set, and we're going to fit our models, and we're going to compute root mean squared error, and we're going to look at those. And then after that, what we're going to do is sort of switch gears and look at the modeler package that allows us to construct those training and testing splits in a more automated fashion, more like an easier to work with sort of an approach, and then we'll sort of try that. So first thing though is cross-validation by hand. What I'm going to do is generate a training data set and a testing data set. So get training and testing data sets. And the way I'm going to do this by hand, there are a lot of ways that you might do this. The way that I'm going to do this by hand is to create first a trained data frame that samples a fixed number of observations from a data frame. And I want to sample from my nonlinear data frame. There are 100 rows in there. I think there should be 100 rows in there. Yep. And I'm going to sample this n equals 80 times. I think. Is it n? Yeah, what is sample n? Oh, size, not n. So if I said size equals 80, okay, great. All right, so my training data frame now, again, has 80 rows. And what I'd like to get next for my testing data frame are the 20 rows in nonlinear data frame that do not appear in training. Right? Again, the way that I'm sort of doing this is to say, I want to take my full data set and put 80 rows over here and 20 rows over here, where those 80 rows are drawn at random and the 20 rows are everything that's left. Right? That's sort of the process that I'm going to use. So what I'm going to do to get my test data frame is a function we don't use all that often, but anti-join. What I'm going to look for in anti-join are the rows that exist here, but not in here. So I want the things that are in the nonlinear data frame and not in my training data frame. And I'll just be clear that the thing that connects these two, the identifying column, is my ID column. So I can just sort of double check. Testing data frame has 20 rows. It has observation 1, 8, 10, 12, 16, 30, 42, and so on. Right? I've drawn this at random. And if we check what's going on in the training data frame, that the IDs aren't in order. But if we, arranged by ID, yes. So 1 is not here, 8 is not here. And if we scrolled farther down, the other things in my testing data frame are not going to appear in my training data set. Okay, so hopefully so far so good. I've taken a full data set and I've partitioned it into a training data set and a testing data set. And my next step is to build models build models of varying degrees of complexity using my training data set and see how well they make predictions on my testing data set. So that's what I'm going to try to do next. So I need to fit 3 models. And sort of getting back to the comment I made at the beginning, this is going to be where things don't always make a ton of sense, and that's fine. Just sort of stick with me. We're gonna see how these models, what kinds of predictions these models produce, and we're going to worry about that a little bit later on. So the first model that I'm gonna get is the linear model, and the linear model is going to be a pretty easy one. I'm just going to say y against x using my training data frame. Great. Hopefully that's all right. The next one that I'm going to use is a smooth model, and this is where, again, if you don't exactly follow what I'm doing, don't worry about it so much. That's not a huge issue. Just bear with me and you'll see what these models produce, and we'll focus on sort of prediction accuracy. So the function that I'm going to use to produce a smooth fit is a generalized additive model. This is coming out of the MGCV package, and the formula that we're going to say is that y is a smooth function of x. I'm not saying quadratic, I'm not saying cubic, I'm not saying anything in particular. I'm just saying it needs to be smooth, and that's it. And I like this approach way better than sort of putting in polynomials or doing something else. I'm not going to go into why, but I do, and maybe you'll remember that later in life, or disagree with me. Who knows? People have opinions. What I'm gonna do though is just try to get a smooth function here, and again, I'm doing this using my train data frame. And then the last thing that I want to do is actually pretty similar. But I want to sort of push this smooth fit too far. So GAM by default is going to try to do its best at getting something that's smooth and runs through the middle of my data points. What I'm going to do is say, let's make this more like you're chasing every single data point, something that's going to be too wiggly. So my wiggly model is also going to come from GAM, and I'm going to say this is a smooth function of x, but I'm going to tell it pretty specifically something about how complex I want that model to be. And I'm going to do something else where I set a parameter that talks about the smoothness here at 10e to the minus 6 and say don't smooth anything, make it as not smooth as possible. And I'm going to say data is train data frame again. So I've got 3 models here, and what I'm going to do next is make sure that I understand exactly what's going on here, right? So can I see what I just did? So what I mean by can I see what I just did, if I take my train data frame and I did a ggplot with x on the x-axis and y on the y-axis, and I do geom point, okay, this is my training data set. And what I'm going to do next is add predictions using this training data frame and the linear model. And remember, what this add predictions function does is add a column of fitted values. And so if I want to see the fitted values in context here, what I'm going to do is geom line, where instead of having the y point on the y-axis, I want the prediction to be on the y-axis. Let's check if this works. No, this doesn't work. Oh, because that's not right. Maybe this works. Right. So great. And I'll sort of emphasize even more what's going on here. Let's say color equals red. Right. So what I'm seeing here is that the way my linear model worked, when I just had a line, it said the best you're going to do is just fit a line that goes sort of through the middle here. It's not capturing any of this. It's doing a bad job here, and it's sort of doing bad over here. But that's what the linear model does. So if I updated this and I said, all right, well, what does the smooth model do? That does better, right? I haven't told it to fit a quadratic. I haven't told it to do anything else. But this intuitively is sort of going through the middle of my data points a little bit better. And now, lastly, again, even if you don't know why this is doing what it's doing, I want to show you what the wiggly model produces. The wiggly model produces something that is too wiggly, right? That it's sort of chasing after individual data points. It's going up here to try to get this. It's dipping down. It's all over the place. This is probably also going to make bad predictions, not for the reason that the linear model made bad predictions, but because it's sort of chasing too much, that the next data set isn't going to have this outlier and it's not going to have this dip. You want something that's going to go more through the middle of everything. Among these, my guess, my intuition, is that the smooth model should do best in terms of prediction accuracy. I'm going to pause real briefly just to sort of point out something that might be useful. If you wanted to add predictions for multiple models at the same time, you can do something like that, where instead of adding predictions, you're going to gather predictions from multiple models: linear model, smooth model, and wiggly model. And if I just sort of take a look at what's going on here when I gather predictions, instead of having 80 rows, I've got 240 rows, and those 240 rows are 80 rows of predictions for the linear model, 80 rows of predictions for the smooth model, and 80 rows of predictions for the wiggly model. And now this mostly works, but if I wanted to sort of separate these things, I might do facet grid, where the thing that I want to facet according to is the model that I care about. Let's take a look. Right, so now I've got linear model, smooth model, wiggly model, and everything is working out, right? And so, again, gather predictions can turn out to be a helpful thing if you want to compare the fits of several models simultaneously. Okay, so the last thing is look at prediction accuracy for each of those, accuracy. And when I say look at prediction accuracy, what I mean is, can we compute the root mean squared error for this model, looking not at the root mean squared error for this data set, but how well it's doing about making predictions on an unobserved data set, data that had nothing to do with estimating this red line. And the way that we're going to do that is looking not at our training data set, but look at root mean squared error using our testing data set. And so if I can compute the fitted value and then subtract that from the observed value and square that and add it up and pull it all together, that's going to be my root mean squared error using the linear model on my testing data set. And that's really the thing that we're interested in. Now, we're not going to do that by hand at all. We're not going to worry about it. What we're going to use is the root mean squared error function that asks for a model that you care about and the data that you are interested in. So the model that we might care about is the linear model, and the data that we care about is not the training data set, but the testing data set. And it computes a root mean squared error that's about 0.7. And I'm getting real close to a point where I'm uneasy with how many times I'm copying and pasting code, but that's not something I'm going to worry so much about right now. So let's look at root mean squared error for the smooth model, 0.22. Cross our fingers here. Let's look at root mean squared error for the wiggly model, 0.37. So what this is saying is roughly, again, what I might expect at the outset, that if you use the red line to make predictions about a future data set, that's not going to work very well because it's missing obvious patterns. And if you use the wiggly model to make predictions about future data, that's not going to work very well either because it's chasing things that are actually noise, not real signal in the data set. And of these three models that we're looking at, the smooth model right there in the middle is the one that seems to be doing the best for this particular training and testing split. We'll try again in a minute to do this across multiple splits to confirm that this is sort of not just due to the what ended up being in testing and what ended up being in training for this particular cross-validation split. We're gonna reiterate that, or we're gonna iterate this a bunch of times. But for now, I just sort of want to say, like, all right, cross-validation is doing about what we would expect it to. It's picking among these three models the smooth one as making the best predictions. And this is great because there isn't some statistical test that we could use in this case. It's not real easy to think of the smooth model as being nested within the linear model. There probably is a test there, but it's not an easy one. And the wiggly model versus the smooth model is even worse. I don't think there's a way that you could plausibly do a hypothesis test comparing the smooth model to the wiggly model. It's just, it's a really difficult thing to do. What we have is something that's more like comparing models using AIC or something like this. We have something like a not getting a p-value. We've got something that is going to be, how do you compare models that are not nested within each other and you still have to pick? And the structure that we're using is prediction accuracy. We're using cross-validation to say whether or not one model is more accurate when it makes predictions about future observations compared to another. So that, I'm really thrilled about this. Cross-validation is just fantastic. Okay, cross-validation is fantastic. And let me knit, sorry, I always, gotta knit, gotta commit, gotta do that part of things. So let's commit all of those. This is cross-validation by hand on non-len df. Sweet. Okay, so now we're going to do, I said we were going to try this a couple of different ways. What we're going to do next is cross-validation using the modeler package. So we started out and we said, all right, I've got my data set and I need to turn this into a training data set and a testing data set. And we did that using a random sample and then anti-join, and that's sort of how we got these things. And if I wanted to do that a bunch of times, I guess I could write a function that generates 100 training testing splits, and each of those are different from each other, and then maybe I could compute my models and I could do all of this stuff on that. And that's sort of what the modeler package tries to automate for you, is that process of generating testing and training data sets, and then we'll have to sort of figure out how we're going to fit models to each of these things. But the way we're going to do this starting out is using a cross-validation data frame, or creating a cross-validation data frame that uses cross-validation MC, and don't worry about why MC, but cross-validation MC on the nonlinear data frame, and I want to have, how many cross-validation runs do I want? Let's do 100, okay? And let's look at what we've produced here. It's a little bit strange, but I've got a data set with 3 columns, train, test, and ID. And let's take a look at what is going on here. What is happening here? So these list columns contain a bunch of things that are called resample. This process that we're doing, cross-validation, and that we'll see in the next video, bootstrapping, is drawing samples from a data set that already exists in a repeated way, and the tidyverse folks call these objects resample objects. So let me just look though at my cross-validation data frame. What happens if I pull out the train column, and let's just do that. So this is giving me a resample object, 79 by 3. Okay, and what I'm going to do next is look at the first element of that list, and it's like a resample thing, and I'll just double check, can I make this be a tibble? Yes, I can. So if I go through all of these steps, if I look at what is a resample object and I force that to be a tibble, it's giving me an object that's got 79 rows and 3 columns, and this is a sample from my original data set. And it looks like it's not drawn everything, so I've got 1, 2, 3, 4, 5, 6. I don't have 7. 7 is probably in the testing data set. I guess I'll double check that real quick. Sorry, the corresponding testing data set. Yeah, I get 7 and then 14 and so on. So the structure of the cross V CVDF is to have 2 list columns side by side, the training data set for a particular split and the testing data set for a particular split and the ID that goes along with that split. And in the next row, you get a different training data set and a different testing data set that corresponds to it, and then the ID that goes along with that as well. Instead of trying to store this as like 100 different data sets, the tidyverse folks are using this resample structure to just sort of store row numbers. If you want to get the full data frames, you can convert it back to tibbles, and that's actually something that we're going to do. Storing it just as row numbers is a little bit more computationally efficient, but it has some other complications that I don't want to deal with. So what we're going to do next is say, yes, we can convert any of these individual objects to data frames. And so now what I want to do is just make sure that I've actually done that. I want to sort of not have list columns of resample objects. I want list columns of just straight good old data frames. And so that's what I'm going to try to next. So cross-validation data frame, CVDF is a new version of CVDF. And what I'm going to do is just go down the list of training data sets and convert everything to a tibble, and go down the list of testing data sets and convert everything to a tibble. So I'm going to do that by saying that train is map across the training data sets and convert everything to a tibble. And then in addition to that, map across the testing data sets and convert everything to a tibble. And I want to be clear, like a big part of the reason that I'm doing this is resample objects you can use those directly in an LM function. You can't put resample objects directly into MGCV's GAM function. And so this step is necessary for the particular kinds of models that I'm fitting. It's not critical for everything, but it is important for the things that I'm trying to do, right? So this is just, if I do this, I'm now back to a sort of a data structure that is a little bit more familiar to me. I still have list columns for training and testing, but those list columns contain just tibbles here and tibbles here. It's a little bit easier to understand. So this is where we're going to start trying to do even more iteration to fit models and compute root mean squared errors. So let's try to fit models and get RMSEs for them. So I'm going to start out with my cross-validation data frame, and I am going to say first, is it possible for me to fit the linear model to every element in my training data column? All right, so I've got a list column. This is a training data set. This is a training data set. This is a training data set. If I fit the linear model to this, I'll get one fit. If I fit it to this, I'll get something that's a little bit different just based on the training and testing split. I'm going to get the same line, but it's going to be a little bit higher, a little bit shallower, something like this. I'm going to get a slightly different fit every single time, and that's what I want to try to get. So let me fit the model, the linear model, to every instance of this. So I'm going to mutate, and I'm going to fit my linear model, and instead of just saying I'm going to fit this once, what I need to do is fit it for each element here. So I'm going to be mapping across the elements in the training data set. So let me map across the train column, and what I'm going to fit, I think I said above, is y against x, where data is whatever element, or sorry, where the training is first this, where the data element is first this and next this and next this. So I'm using this sort of dot x is train, use that dot x as a placeholder, plug it in over here, and fit my linear model each time. And I'm just going to double check. I'm going to run this code and see what happens. And what it produces here is a list column with linear models. And let me just sort of, again, let me pull out the linear model list column. And what I get is a linear model fit, intercept and slope every time. It's a little bit different from one iteration to the next, again, given the variability in what's in my training data set and what's in my testing data set, but I'm getting those fits every single time. And so what I'm going to do next is try to do similar things with the smooth fit and the wiggly fit. So I'm just sort of checking. I had GAM smooth, train DF, and then GAM smooth with some other stuff. So let's try to recreate that. So let's get my smooth models. I'm still going to map across the training column, and I'm going to say I'm fitting a GAM where y is a smooth function of x, and my data is that dot x placeholder. Okay. So again, I'm going to take my first training data set and plug it in here and fit a smooth fit. Again, I'm just going to check, does this work? Takes a little bit more time, but yes, it's still working, and I'm getting GAM fits instead of LM fits each time. Now I'm going to do the same thing with my wiggly model. I'm going to map across my training data sets. I'm going to fit a GAM where I still say y is a smooth function of x, but I'm doing this k equals 30 business and saying sp is 10 e to the minus 6. And now finally I'm saying that data is whatever that dot x element is. So I'm going to check this, see if it runs, make sure everything is fine. It takes a minute, it's fitting a bunch of models. But I'm left with now linear model, smooth model, wiggly model. Everything is sort of working here. The next thing that we can do is, that we need to do, is produce the root mean squared errors that goes along with this. And I guess I've got a couple of options here. The couple of options that I have, I can first sort of say, let me take this testing set and this model and produce a column. I can take this testing set and this model and produce a column. I can take this testing data set and this model and like produce a column. But what I'm saying is I can combine each testing with each model separately and get sort of 3 columns. We could probably do like a unnesting thing where you just get like a column of models and then you sort of do root mean squared error across that way. That I'm not going to worry so much about. So what I'm going to do, I'm putting in an extra step here, even though I guess it could all be part of the same thing. But I'm starting a new mutate just to sort of be clear that what I'm computing is root mean squared errors for my linear model. And the way that I'm going to compute root mean squared errors for my linear model, again, is to say, give me the testing data set and this linear model and produce the root mean squared errors. I've got 2 arguments going in here. And since I have 2 arguments going in here, I can't just use map. I've got to use map2, where I tell it, let me sort of make sure how root mean squared error works. The first is the model, and the second is the data set. So I'm going to say my first argument .x is linear model, and my second element .y is the testing data set, and I'm looking at root mean squared error of model is .x and data is .y, right? So this is a complicated, again, complicated. I'm mapping across 2 things, and I'm fitting a root mean, or getting the root mean squared error for the .x linear model, taking this element, and the .y data set, this element, and then I'm moving on to the next row and extracting this for .x and this for .y and refitting, okay? So again, I'm just going to sort of double check here that this all works. It does, and what I'm left with is a collection of root mean squared errors for the linear model. And this is all just numbers. It's producing some number here, some number here, some number here. So I'm going to tell it, instead of giving me a list, just give me those numbers. Gonna fit. Okay, so it's giving me root mean squared error for the first linear model. When I apply that linear model to the testing data set, I get a root mean squared error of 0.8, then 0.6, then 0.6, then 0.8, then 0.6, then 0.7, and so on. Okay, so now I need to repeat this process for the other 2 models that I care about. So if I say, instead of plugging in the linear model, if I plug in the smooth model, how does this work? And if I plug in my wiggly model instead of my smooth model, how does this work? Now again, this is not, this is not my favorite code. I'm copying and pasting things multiple times. There are probably ways that I could do this. For right now, I think given how sort of weird this whole process is likely to be if this is the first time you're working on cross-validation, I'm okay with this code being like not optimal in some ways. I don't love copy and pasting all this many times, but whatever, that's not sort of our biggest focus right now. So let me just sort of, I'm going to save the results of this. Let's do cvdf. I'm overwriting this thing several times now. So let's take this and just save the whole results. Okay, it takes not that long to run. Let me see what's inside of here. Oh, I didn't see. This is the problem with copy and pasting. I didn't do it right. I need to make sure that I get different columns for different root mean squared errors. Okay, so now let me double check that I've got something that's right. All right, so now I've got a column, root mean squared error linear, root mean squared error smooth, and root mean squared error wiggly. And these numbers all look bigger than these numbers, and mostly these numbers look smaller than these numbers, but it's not always true, even right here at the beginning. The wiggly one sometimes works a little bit better, and the question is, in general, which of these 2 models is the most appropriate here? So that's what we'll do next. What do these results say about the model choice? So the way I'm going to do this is take my CV data frame, and I'm really just going to focus on the root mean squared errors. So let me get select starts with RMSE. All right, just get those columns. Okay, and right now I've got RMSEs for 3 different models side by side. This is not a tidy data set at all. And again, there are ways that we might have up here pivoted in something and then mapped in a different way. now, like, we put off that problem then, and now we sort of do have to address it. So I've got a root mean squared error for linear and smooth and wiggly. This is not exactly the way that I want this to work, so I'm going to pivot longer to get a tidy data set, and I'm pivoting all of the columns, and the names are going to turn into the model that I fit, and the values are going to turn into the root mean squared errors. So now I'll have a column that says the model is values RMSE linear, smooth, and wiggly. And next to that I get the actual RMSEs. And I'm going to get rid of the RMSE part here. So I can say what names prefix is RMSE underscore. Okay, so now I get the linear, smooth, and wiggly root mean squared error in each of these. I've got 300 of those, 100 cross-validation training testing splits, and 3 models fit to each of those 100 splits. Whew, this is getting great. So what I'm going to do next is try to make a plot of this. Let's put on my x-axis the model that I care about, and on the y-axis the root mean squared error. And let's do, come on, a geom violin. And just see what this looks like. All right, so this is kind of cool because what I have is the distribution across 100 training testing splits fitting the linear model, the smooth model, and this wiggly model. And we had seen, just looking at the plots, it looked like the root mean square, or sorry, it looked like the linear model was doing worse, and it is always making worse prediction accuracy, worse predictions on the testing data set, always worse linear than smooth or wiggly. The smooth and wiggly, those are both at least in the right neighborhood, right? The smooth one is doing better on average, in general. The smooth does better than the wiggly fit, but the wiggly one is clearly better than the linear model. Now again, there are no p-values that go along with this, but based on this distribution of root mean squared errors and on like the plots of the models that we have seen up to this point, this is all sort of pretty good evidence that among the 3 models that we're using to fit through this cloud of points, the smooth model is doing the best. And that's pretty neat. That's pretty great. We could, I suppose, also compute averages. So what I mean by that is if I do all of this and then I group by model and summarize average root mean squared error is the mean of RMSE, we can see that a little bit more clearly. The average here is 0.71. 0.289 looks about right, and then 0.35. So average is doing great. Looking at this distribution, I think, helps because it shows there is some overlap between these two things. It's not always the case that the smooth does better. There's some overlap here, but we're doing all right. So this sort of figure, again, is sort of mapping not complex enough and too complex, and we're seeing high prediction errors and high-ish prediction errors with sort of the sweet spot being right there in the middle. So that's all, man, I'm real excited about this. So let me knit again. Okay. What I have next, what I next? I need to commit first. So we did cross validation using modeler. I was right the first time. Okay. All right, so what we're going to do next is try this on a real data set. So try on a real data set. And what the sort of the thing that I want to get out of this is illustrating that model selection is not always so straightforward, right? So that's what we're going to try to do. And the real data set I actually already put into a data directory in my project. So here I've got a data directory, and I've got a Nepalese children's CSV. There was a study a while back that evaluated was looking at sort of the growth and health of children in Nepal over a period of time. We're looking at a cross-sectional version of this data set. We don't have to worry about like following these kids over time. We're just going to take a look at two variables, how much the child weighs and what their arm circumference is. The sort of relationship between those two things gives you some idea about the extent to which a child is sort of growing in a healthy way. And that's what we're going to look at. So I need to import my data. So what am I going to call this? The child growth data set. And this is going to be read CSV in my data directory. What did I call it? Nepalese children.csv. And it turns out this is already a pretty tidy data set. All the variables are nicely named. I've got age, sex, weight, height, arm circumference. Sex is not that tidy. It's been coded as 1 and 2, and we would have to go back and figure out like, well, what's a 1 and what's a 2, right? But we're not going to worry about this as a predictor, so I'm just going to note that that's an issue. What we're going to worry about is how well weight predicts arm circumference. So let's take a look at that. So weight versus arm circumference. Okay, so I need to take my child growth data frame and let's just make a plot to see what we're looking at. ggplot, on the x-axis I have weight, on the y-axis I have arm circumference, and let's add some points here. Let's add some points with alpha equals 0.3. All right, so just sort of taking a look at this, it's pretty clear that there is an association between weight and arm circumference. Generally speaking, the children who have heavier weights also have larger arm circumferences. In the bulk of my sort of data potato going on here, I've got like what looks sort of like a line, maybe. Maybe it sort of does something twisty up this way. If you look at it, maybe it sort of is like flat and then dips up. And there's also down at this end, it looks like maybe there's like some non-linearity, something that sort of, you know, curves down this way. Okay, so that's sort of what we have to deal with. And the models that I want to compare first is a linear model, which sort of like the other one, I don't think the linear model is going to work all that well. And when I say linear model, I mean just a straight line through the data points. Everything we're considering is a linear model. This is just going straight through the data points. The next one that I'm going to consider is a variation on that, where instead of going straight through the linear model, I do one piece that's sort of straight, and then I can allow this to change a little bit, and then I get to be straight again. And so what I'm hoping there is that we'll see something like maybe there's an uptick this way, and then eventually it sort of flattens out. But both of those are going to be like flat pieces. I'm going to get a change point in the middle. And then the next thing I'm gonna revisit that GAN thing and just fit a smooth curve that goes to the middle and see what happens. Okay. So again, as we're fitting these models, it's less important that you understand exactly how each piece works. Mostly what we want to look at are, if you just look at the fits and then you try to decide between them using cross-validation, what is the conclusion that you would draw? So I need to do one bit of additional data manipulation. If I want to fit this sort of piecewise linear thing, something that's flat and then flat but with a different slope, I need to update my data set. So what I'm going to say here is if I want a weight change point, what I need to fit is, or what I'm going to do is ask whether or not weight is greater than 7, and then I'm going to multiply that by weight minus 7. And again, if you're not familiar with change point models, why exactly I'm choosing these two things might not make a ton of sense, but as we'll see in just a minute, this is going to give me something that's flat up until 7 and then flat after 7, and that's the change point model that I'm interested in. So there's that. Everything's great. Okay, so let's try to fit the models I care about. The first of these, like I said, is going to be a linear model, and this is going to be, what is it? LM arm circumference against weight, and my data is child growth data frame. I'm not doing any cross-validation here yet. I just sort of want to see how these different models fit to the data that I'm interested in. I'm also going to do a smooth model that is a GAM for arm circumference as a smooth function of weight. I'm not playing around with any of this K or SP business, and I'm still using data is child growth DF. And then the piecewise linear model is going to be a linear model here where I use arm circumference against weight and also the weight change point variable that I constructed just a minute ago using the data is child growth data frame. So I've got three models here: linear model, piecewise linear model, and smooth model. And I'm going to try, gosh, it's been a while. I'm going to try something like this again, where I'm just gathering predictions and then making some plots. So I need to get the child data frame, gather predictions from each of these three different things, and then make a plot. Okay. So let me get my child growth data frame, gather predictions from the linear model, the piecewise linear model, and the smooth model. And then let me double check that this works. Yeah, I've got model, linear model. I've got 3 times as many rows as I started out with, and I've got a prediction column. And what I want to make is a ggplot where on the x-axis I have weight, on the y-axis I have arm circumference. Yep. And then I'm going to add points, geom point with alpha equals 0.3. Oh, that was the wrong hotkeys. And then, still not right. And then I'm going to add a geom line where instead of looking at the arm circumference, I'm looking at the predictions. And I'll just sort of stick with, you know, color is red here. And then let's do facet wrap, facet grid. I don't think it matters. Facet grid, everything against the model that I care about, right? So I'm trying to produce that same graphic that I had above where I sort of showed a line and then a curve thing and then a wiggly bit. This is what I'm trying to show here with the child growth data frame. And I did something wrong. What did I do wrong? Let me start out and see, does this work? It says arm not found, arm circumference. So let's try this again. Okay, now let's try this. Mapping must be created. Oh, okay. All right, great. Okay, so I'm gonna zoom in just to like really try to do a comparison of these. So in this fit, I've done 3 things. So I've got this linear model that is going straight through the middle of the data potato, and it's missing some of the stuff that's happening down over here. And I'm also maybe missing a little bit that's happening up in this end. The piecewise linear model, like I said, what I've accomplished here is that I've got a straight line for this, and then I've got another straight line here, but those 2 things have different slopes. I've changed at a change point at weight equals 7, I've gone from one slope to another slope, and I'm getting sort of a fit that maybe captures some of this nonlinearity. And then the smooth model is sort of the most flexible of these. It's sort of giving me something that goes kind of curve that goes mostly through the middle of these data points. And there's some overlap, it looks like, in the shape here and the shape here, but not precise overlap. This is doing something that's a little bit different. Okay, but these are the 3 models that we would like to compare for this data set and ask which of these is going to be most appropriate for making predictions, or which of these, in a broader sense, which of these is the right model to use for this association. And so what we're going to do, if we're asking which of these is the right one to use, what we're going to do next is try to do that cross-validation procedure. Now, a lot of what I'm going to do now is the same thing that we did in the simulated data set, just changing out some model specifications. So I'm going to run through it a little bit more quickly this time, but we'll sort of see how this goes. So let's try to understand model fit using cross-validation. So the first thing that I'm going to do is I'm just going to call this again my cross-validation data frame, and I'm going to start with the cross v MC applied to the child growth data set, and I want 100 of these. And as before, I'm going to map across the training data set. I'm going to mutate and map across the training data set and convert everything to a tibble. Again, this is important. This is something I have to do because I'm fitting this GAM model. You wouldn't have to do this otherwise. And this is going to be not super computationally efficient in comparison to leaving everything as a resample object. But because I want to fit a smooth curve, I think this is a necessary step. So here's my cross VDF. I've got training and testing data sets every time, 2,000 odd rows here and 500 odd rows here. And I've got 100 of each of those. And maybe what I'm going to try to do next is copy and paste, again, in hopes of saving time. So here I'm going to take all of these and let's see if I can fit the models to the splits. All right, so I'm going to fit, I've got a linear model across train, and I'm going to map, instead of y, I've got arm circumference, and the predictor is weight. And I'm doing the same thing for the smooth model, arm circumference against a smooth function of weight. And I'm not fitting this wiggly model anymore. What I'm fitting is a piecewise linear model, which is mapping across my training data sets and fitting a linear model of arm circumference against weight and weight change point, using the .x placeholder for my data set. I'm gonna make sure I've got commas in the right places. This is why copy and pasting code always makes me a little bit nervous. Does everything sort of look like it is supposed to? Close. I'm just going to run this and see what happens. It's going to take a minute because I'm fitting a bunch of models to a bunch of data sets. I didn't get any errors. That's not exactly the same as saying that everything is right. But I'm crossing my fingers here. I guess maybe I'll double check that, if I pull piecewise linear model, that I get output that is roughly right. So if I pull each of those, I get a linear model. I get coefficients for intercept, for weight, and for the change point. Intercept, weight, and change point, they're changing a little bit. I'm happy with this. I think this is mostly working. So I'm going to do a similar process here. I'm going to get rid of the wiggly model, and I'm going to add a row for my piecewise linear root mean squared errors. And I'm mapping, instead of across the linear model, I'm mapping across here, piecewise linear, so root mean squared error linear model testing data set, and gives me a root mean squared error. I think this is all going to be a little bit easier to make sure that this is right. Map double each time. Okay, so that's doing pretty good. And then the last thing that I'm going to copy and paste, I think, is this one, which is the violin plot of root mean squared errors. So violin plot of RMSEs. Root mean squared error starts with RMSE, gives me each of those. Pivot, wider, linear, piecewise linear, and smooth. I don't even have to change anything in this code. This is doing great. And let's take a look. Ooh, this is a lot closer. This is a lot closer than the other one. And I think this is why very often model selection in practice is not so easy, because I've got three different kinds of fits, right? I've got one that's a straight line, one that's piecewise linear, and one that's smooth. And now I have to pick in a way, at least in this instance, that is not entirely driven by p-values. You could compare this model to this model using a hypothesis test. But that hypothesis test depends on having like a change point at 7. You couldn't compare a change point at 7 to a change point at 8, right? There's some element of this where there's not a way to do a hypothesis test that's going to work real well. And then similarly, if you wanted to compare either of these to the smooth model, that's just not going to be possible using a p-value either. So we could look at some other metrics, and we're looking at root mean squared error. And in terms of root mean squared error, the linear model does okay. The piecewise linear model does better pretty consistently. I think this seems like it is a real improvement in prediction accuracy. The smooth model probably does a little bit better still. It's a little bit shifted down, just a tiny bit. We could compute the averages also if we wanted to. But the question at the end of the day is going to be, which of these models are you going to pick? Which of these models are you going to use? And I'm going to pause for like 5 seconds and hope that you stop and you think a little bit. And if you're following along, you click back and forth between these and you think about which one you like. So here's my pause. Okay, so I hope you have decided which one you would pick. For me, I would probably, in the end, pick the piecewise linear model. And the reason for that is the following. This is maybe a little bit unfair if you're not sort of super familiar with piecewise linear models or smooth models or whatever, right? But I think in terms of root mean squared error, there is a clear improvement going from a linear model to a piecewise linear model. There is some additional improvement using a smooth model, and that's something that I would keep in mind, but it's not a huge improvement, right? And the reason probably that I would pick a piecewise linear model here is that the interpretations of piecewise linear models are a little bit more straightforward than they are for smooth models. Here I've got a line with a slope, and I can talk about the expected change in y for a 1 unit change in x. And here I can talk about the expected change in y for a 1 unit change in x. And I can talk about whether there's a real difference there, right? Like those are things that I could, at least in principle, try to talk about. The smooth model is more correct, but probably harder to interpret. And I think where exactly I would come down between these two fits, I think depends on how much I care about like really squeezing the most out of my prediction accuracy versus having something that's going to be a little bit easier to interpret or to explain or something like this. And that, probably depends on where, are you trying to publish this? Are you posting it on a blog, or is it just like a quick exploration? And I haven't touched any of the other variables in my data set yet. So if I really needed to worry about this, there would be some other things that are complex here. But I guess, again, at the end of the day, or at the end of the video, at least, what I want to drive home is that the choice among models is not always super direct. And it requires a little bit of thought, a little bit of nuance, a little bit of sort of taking a step back and evaluating why you're building a model in the first place, how well do models work, and what are the trade-offs that you're willing to make among things. So that's all I'm going to say about cross-validation. Again, I hope you have sort of followed along. If what you get at the end of this is that you can sort of look at these and say, all right, I understand one of these models is making better predictions. I don't know exactly how this model works. I don't know exactly how this model works. Exactly how those work isn't the point. What is the point is, do you understand that we're looking at prediction accuracy and how we're measuring prediction accuracy using cross-validation? And if you've gotten that, then great work. And I appreciate you following along and sticking with me. Awesome. Thank you very much.